Okay. So this presentation is about piezoelectric energy harvesting interface circuit using bias flip rectifier and shared inductor. So we're going to discuss about it today. So piezoelectric energy harvester. So basically, it works like this. So there is a mechanical circuit that we can see over here. So this from here we can turn it into electrical current via this circuit, and this whole thing can be interpreted as this one single thing, where this mechanical part can be interpreted as a current source, and there is capacitor and a resistor in parallel, and this is a piezo harvester. So in the commonly used harvesters, the IP, the current source here, is a sinusoidal current source with the equation IP equal to IP sine omega t, where omega is 2 pi f. So since the output is sinusoidal currents, we need to rectify this current rectify the voltage before using it in circuits. So the three most commonly used rectifiers are full bridge or full wave rectifier with voltage doubler and switch only rectifier. Full bridge rectifier, which looks like this. Here we connect the piezoelectric harvester with the full bridge rectifier, as you can see over here. There is this capacitor, which is denoted as CREC. So the diodes are assumed to be constant voltage model diodes. The constant voltage model diodes actually, actually works like this. So they are off until the diode voltage reaches a certain voltage, in which case they turn on. This voltage is called VD. So this is the constant voltage diode. So until the VBR here, this voltage right here. So until VBR is equal to Vrec plus VD, these diodes are turned off, and no current actually flows through this capacitor. And when V break actually exceeds this limit, the current starts to flow until IP changes direction.
Sorry. Is this here Vrec plus 2VD?
Oh yeah, sorry. This is 2VD, right? So this is 2VD. Yeah. So let us see in more detail. So yeah, it should be 2VD, as we can see in this graph as well. So the shaded regions actually represent that. So while this current flows, firstly, this capacitor will charge, the CP will charge, and once the CP is charged, and then the current will actually flow into the diodes. So the shaded regions actually represent the charge that does not flow into the output. At that time, the CP is actually charged. So when Vrec is low, then most of the charges actually flow into the output, but the voltage itself is pretty low. But on the other hand, when Vrec is high, almost no charge actually flows into the output, as you can see from this graph. So we can actually write the equation for the power, that is for the power, which will be like this, where PP is basically this identity, and we can actually determine for what value of Vrec, as we can see that the power is actually dependent on the voltage. So we can get a maximum power for a certain voltage, and that voltage is given by this equation. Then it is voltage doubler. So due to the negative half cycle, the voltage across the harvester remains constant and no current actually flows into the output. So as you can see, when the current is negative, no current actually flows into the output. On the other hand, when the voltage is positive, the current is positive, the capacitor charges until Vrec plus VD, and then the rest of the charge actually flows into the output. So the equation for power for this voltage doubler will actually look like this, and Prec will be max for Vrec equal to Vp minus Vd. Observation. So if you look at these two equations, the maximum power obtained in both full wave rectifier and voltage doubler, we can see that if we assume an ideal diodes where Vd is equal to 0, the maximum power is the same for both cases. but it's not the case for not a non-ideal model, for example, constant voltage model, in which case the voltage doubler gives actually a better output, a slightly better output than the full wave rectifier. Then we come to the theoretical maximum power. So we can actually determine the theoretical maximum power of this piezo harvester can actually produce. This is actually fairly easy, which looks like this. And then if we take the ratio of the maximum power we get by full bridge rectifier or voltage doubler and the theoretical maximum power, then that ratio will actually look like this. And then if we actually plug in the values, we'll actually see that it's only 12.5% of the theoretical maximum that we can actually obtain. So we need to improve on that. So how can we do that? So the one solution is switch-only rectifier. A switch-only rectifier, so if we have to see that in full bridge rectifier, we can actually provide charge to the output in both positive and negative half cycle. If we go back to the full wave rectifier, in both positive and the negative half cycle, charge was actually delivered to the output. On the other hand, voltage doubler, in the voltage doubler, in the negative, when the current was negative, no charge actually flowed to the output. But in the positive half cycle, it needed to do only half the work to charge the CP. So if we can actually merge these two advantages, then we can actually increase our power output. And so that's where this switch only rectifier comes in, where we actually connect this switch over here, and this switch turns on only when IP is equal, it becomes 0. So when IP becomes 0, the switch momentarily turns on. So as you can see over here, these are the spikes when the switch is actually turned on, and as you can see over here, when the switch turns on, immediately CP is discharged to the ground. So here are the points where CP is discharged to the ground. So after that, every time basically there will be no charge flow into the output until the CP is recharged to Vrec plus 2 VD. So this actually decreases the time that the charge is not flowing into the output by a lot, and that's why we get more charge into the output. So we can see over here the power equation in the output for switch only rectifier would look like this. The power will be maximum for this voltage, and therefore we actually get that the maximum power is actually like this. And if we assume this, that BP is much greater than BD, we actually see that the power drawn by switch only rectifier is almost double of the full bridge rectifier or voltage doubler. Then we can actually improve this even further. Even though switch only rectifier was better, even it had its own problems, that there was still some charge loss, as we still have to charge the CP. So we can actually decrease the loss even further by using an inductor with the switch. So as we use the inductor, when the switch is turned on, remember when the current is 0, the switch turns on. In that moment, the inductor will actually flip the voltage of the capacitor, and after the flipping, only the work IP needs to do is to make CP's voltage to this VP plus 2 VD, which is actually pretty easy, and so it takes a lot less time, and so the energy loss also becomes much lesser. So here are the graphs. So as you can see over here, that once the voltage of CP is flipped after the switch is turned on, we only need to only for this amount of time CP is actually charged. So for only this amount of time, there is no charge into the output. Otherwise, there is charge into the output all the time. So our power output is actually increasing by a lot. So the final voltage across CP after flipping is actually look like this. This is basically the amplitude of the flipped voltage, which looks like this, where these are the equations of tau and bit of tau, and then we use a beta here, which looks like this, and the power equation actually looks like this over here. So let's take a deep look into the power equation. So the power equation, so in the power equation previously, we did not take the RP into account. So this power equation is without taking the RP into account. So if we take the RP into account, this is the equation that we get, where the terms used here are new KBF and omega P T1, which look like this. And then we get the maximum power output Vrect max, which will look like this. And then if we plug in, we will get the maximum power output for the maximum power output. And this QBF over here is actually this. Then again, we talk about the theoretical maximum power once again here. So first of all, the ratio will actually look like this for the bias flip rectifier. And remember, sorry, this is for the full bridge rectifier. This is for the full bridge rectifier, and this is for the bias flip rectifier. This is the ratio. And then if we actually like a quick look at the bias flip and the full bridge rectifier ratio, this is the ratio that we obtain. And then if we actually plug in some values over here, C, R, and V, these values, if we actually plug in, we actually see that we have almost a 3.29 times improvement in the bias flip rectifier, assuming ideal diodes. And even if we don't assume ideal diodes, our improvement becomes 5.46%. And if we assume a perfect flipping, for perfect flipping, tau has to be equal to 0. So immediately the voltage of the CP has to flip. So if we assume the perfect flipping, 81% of the theoretical maximum power is actually obtained by the bias flip rectifier. Thank you. That's the end of the slides.
Okay, thank you. Can you go to page 14?
14, okay.
Taking RP into account in the equation where RP, I don't see RP in the power equation. Maybe it here in back. Go back. Is RP in omega exchange frequency, right? Beta is R, right? Rectifier. So normally people will ignore RP. No, it is different. RPF here is rectified. Where RP different, right?
RBF is the entire resistance between this from this inductor to this like CP. So this entire path resistance is like RBF.
RP is only piezo resistor, right? The parallel.
Yeah, the RP is the resistor.
In next slide, when taking RP into calculation, why I don't see RP in this equation?
Yeah, I actually like as far as I understood from the paper, like they just state that after we take RP into account, this is the equation we get. But although
so what difference between having RP and don't have RP? Let me check. Maybe next semester you can answer the question by to save our time. So now you cannot answer right away, right?
Actually, here it is written like this: the our resistance RP has not been taken into account till now. Without this resistance, the source should be capable of providing any amount of power without limitation. So yeah, the derivation for the output power in the presence of RP is provided. Oh, sorry, this is not this equation. Actually, I actually
Without RP, right? Not taking
this is
out RP, right?
yeah, this is not this equation. This is this is a equation in appendix B. Sorry.
So having RP, the equation should be different, and right?
Yeah, that should contain RP, right?
So after, so how do you think we can have the for bias rectifier? How we can get the maximum power?
I mean, like, how do you get the maximum power output?
Yeah. When you design a bias rectifier, what should you consider to have the most as much as possible power can be harvested?
Okay, so I can put in this equation over here. First of all, like okay. So first of all, like it's directly proportional to CP. So more CP will mean more power, and then it's more directly proportional to FP. So more frequency of this current will mean more power, and then VP was like if we go back. So VP is actually proportional to IP and the frequency. So basically more I, more C, and more frequency will mean more power. And finally, if we see over here that the relation is direct is also so the Virac for the Virac, this is the value of the Virac that we actually get the maximum amount of power.
Yeah. Actually, when I buy a flip rectifier, we only control rectifier voltage, and
so Virac.
right. Other thing is the TP. T
okay,
time.
So you cannot really control the piezoelectric current.
Right. CP and other CP and frequency is fixed normally.
So basically you cannot control this part.
Actually, IPJT chain, IP chain, but CP fixed, CP RP fixed, and frequency also. It is mechanical. So frequency can change by changing your mechanical position of PAT. So I will show you. Let me share.
So I prefer stop my share.
Yeah. Do you see my screen?
Yeah.
here. So here is the real piezo I'm using. Frequency is can be changed by, you might change your mask on you. If you change the mask, you put on the PAT, you can change frequency, or you can change the clamp position here. So from the clamp to the tip mat, it will vibrate, right? The rest will be fixed. So if you change the clamp position, mean you change the length of the PJT, so it will change frequency. But normally during operation, we don't, it's difficult to change clamp, right? It is mechanical. So normally in the design, we will fix frequency, and CP also fixed. So in the data sheet of the piezo, we will have the capacitance. In here, I'm using 20 nanofarad. Okay, let's go back to your slide.
Okay.
Actually, I have your slide. Wait.
Okay, I'll show that.
So,
I have a question.
yeah.
So here in the voltage doubler, so in the positive half cycle, so if we go to the voltage doubler, in the positive half cycle, to take it from here to Vrec plus Vd, it only needs to do half the work. So it's basically discharged. So the capacitor is discharged. So in order to charge this, we only need to do half the work. Why?
Can you speak again? Talk again.
So it's saying that in the positive half cycle, to charge this capacitor, we only need to do half the work. The amount of work becomes half. Why?
Positive half cycle. And then
in the voltage doubler, in the positive half cycle, to charge the capacitor, we only need to do half the work. Why?
Half the work? What do you mean?
Yeah. The amount of work. Energy, basically, the amount of energy is half. The amount of energy wasted in this capacitor.
Because you only charge your CP from minus VD to Vrec plus VD, right? Why in your full rectifier you have to charge from minus Vrec plus to VD? So the voltage you have to charge from full rectifier from minus Vrec plus to VD to Vrec plus to VD is double, right? Double here, right? The voltage difference here is Vrec plus VD minus VD. It means you have to charge the voltage difference is Vrec plus to VD. But here the voltage difference is 2 Vrec plus 4 VD. It is double. So right.
Okay.
So it's like double current to charge here compared to voltage doubler, right?
Okay.
Anything else?
Oh, okay. I see.
And in bias rectifier, in here you can improve power by changing your time you buy a flip time T, right?
Mm-hmm.
In
Yeah,
here,
the tau. The better the tau,
yeah,
less the tau, the more power we get.
yeah, right. And it can change by change the inductor. You can change inductor value.
Mm-hmm.
So if you see in the paper, here is a graph showing the output power, and with the chain of inductor value, you can see the more the larger inductor value, the larger power can be harvested, right?
Mm-hmm.
Yeah. So when design, we can change inductor or we can change the voltage of rectifier. What the two ways we can control. However, the trade-off between inductor values and the size of the system. So inductor increase, but the size of system will increase. So that is an issue. And other people will try to solve the issues. Yeah. So did you try to calculate? Did you try to calculate based your power based on the equation? Did you try to calculate the power based on the equation and the values they provide in the paper?
No.
So next week, your work is to calculate it, right? Now you have equation, and then you calculate by yourself and compare with their results, right?
Okay.
They show results, but you have to calculate to make sure it's correct.
Which results? Like I have to compare with which results?
So let's see. So in here, they have power with diode with. In here have 1, 2, 3, only 3 figures. So you will calculate like these 3 figures, right? That is
for these figures for different values, I will actually calculate different. I will actually plug in this equation and then see what I get.
Yeah, you calculate by yourself and compare with this plot.
Okay.
Here they plot, but you have to check it with your own calculation. And if you can calculate fast, and then you can start with simulation, right? I already set up simulation for you.
All
So it have full rate rectifier here, switch only here, and bias flip here. Do you still remember how to simulate? So I will explain again. So you might forward. So first you open this tab, right, to run simulation. To run simulation, you click run. Yeah. Okay. It finished, so you can check the waveform. Here is, I already saved on the waveform, but if you want to see one waveform, you click results and direct cross and main form, and then click add to output to save the plot. So for example, here I see this one thing, I click to this line, and then you can see the waveform here. And if you want to see the current, first you have to save the node you want to see. For example, here I save the node, so you can see the current through this node. However, want to see current, you have to go to tune, and then click calculator, and then click into IT to check the current. Click IT, and then you click in the node you want to see the current. Click here. Here is the current you want to see. So click here to plot the current, and here is the current. However, if you want to save the current to see later, and then you will go to this, click setup output, and then click get equation and save the current here, for example, IPIT, and then click add here, and then IPIT will be saved here, right? And next time you can just plot, and you can see IPIT. Okay, that is how you see the current. And in the top, I also set up the value here. F, a frequency is, here is a current source. Current source here in this library, analog library, that name iSync, it is assigned current. So we have frequency. I name it F, and the amplitude is IPIT. So you can change the frequency here, for example, 100, and you can change the IPIT here is 42 microfarad, ampere, and then in bioflip rectifier, you can change the value of inductor. I name it L, and the resistance of the inductor, right? So in here you can see yeah, you can see the waveform different between full rate rectifier, split only, and bioflip. It is same as the theory. So here, if you want to see the power, here I only save it. But if you want to calculate power, you go to tune, calculator, and then you click here to see to take your current flow into output. Use Ctrl C, and then click voltage, and then you hit it. You multiply. Here is current multiply voltage, and then you click leave. It will see the start time from 0 to 100 millisecond, and then OK. Then you click average. It will take your average power, right, from 0 second to 100 millisecond, and then you go there and then get equation, and then you can save your power. In here, your full rate rectifier is 8 microwatt, and read only is 17, and bias fit is 26. So if you want to simulate like this graph, you have to change your voltage rectifier voltage, right? In here, I set the rectifier voltage at VR. This will set the voltage of rectifier. So you can do it by using parametric analysis. So then you can click V out, and then you can change the swap your voltage. For example, from 0 to 2 volt. In here, from 0 to 2 volt, linear step. So maybe you change 500 millivolt. I want only plot your power. Here, okay. So let's run. So if you run in here, you only run with one value of V out, but with parametric analysis, you can change different V out. So it's like it automatically change. In here, you can see V out automatically change, and then you can swap, right? Now you can see your power here, and here is the V out you change, right? Do you understand?
Yes, like I will have to watch the recording again. Like it's a big process.
Yeah. You can simulate.
Okay.
Okay. Okay. Do you have any question about your simulation?
I was like, so I have to simulate the pass flip rectifier and then replicate the result in the paper, right?
Right. You simulate and check.
Then, okay, I bring up the same result. Okay.
Yeah. You have to make plot like this, but by your own simulation, right?
Okay.
In here, I did not set the values similar to paper. You have to change it, right? You have to check it. Any questions?
Can you show the how you like set the the axis again, like in the vertical axis power, the horizontal axis voltage? How did you do that?
This power axis,
Yes, yes, yes.
actually it automatically change because I already saved the power here, right?
Mhm.
So, for example, here, for example, I run here.
Mhm.
I click on here. So it's only have one values of V out is in 1.2 volt, right?
Mhm.
So it's only have one values of P rectifier, P switch, P bias. It's only have one value.
Okay.
However, when you run parametric analysis, it actually change the values of V out. It's like you run the simulation multiple times, right?
Mhm.
So it run after it's run on the values of V out, it will automatically plot on the values in different runs, right? So for example, first you run 0, so its own values here will be 0, 0, 0, right? It will plot here, and then it will run 0.5. So value will be here and here and here. So it's automatically plot like this. You don't need to do anything. What you do is to change the values of V out here, right?
Oh, okay. Yeah. How do you bring this window up? Like the
Yeah, you can run and similar to this paper, you can run values from the out from 0 to 5 and check, right?
Okay. Okay.
Anything else?
I don't think so.
Hi, do you have any question about simulation?
No,
Yeah, I used to have
by the way,
has a little bit, so I don't have any questions.
So I already recorded. You can watch after meeting. You can
yeah,
watch.
upload the recording.
Yeah. You can look at it and do.
I have tried to draw a diagram ranging the value of the signal like liner step in the software.
Okay. I think that's all for today. If you have any question, you can ask later, right?
Yes.
Okay.
I have a question. Sorry, I have a question. Should I, because I don't have background in the CMOS and fast, so should I focus about 1 week for the knowledge?
Actually, in this bio flip, you don't need to have any knowledge of CMOS, right?
Yeah. You don't need to have any knowledge of CMOS actually.
Here is like a switch, just turn on and turn off.
Yes.
You don't take any values of CMOS in here, right?
Yes.
I for Thai, I will send the test band for you later because here is only for Ryan Caden, so I will send you this schematic later. Okay.
Okay, thank you.
Okay. Okay.
Yeah.
Any questions? If don't have any question, okay, let's stop here. See you next week.
Yes. Good night.
Okay.
Thank you.
Bye.
Bye.
Thank you.
Good night.
Thank you. Goodbye. See you.